Brian said he's going to be driving the bus. We're going to be looking at A-star pathing.
Yep, we're going to do pathfinding. So, before we get started, Thomas, what do you think about that E3s?
Oh, so good. So good. I'm a huge E3 fanboy. Last year I took off work. Luckily this year I didn't really have to because we all got together and watched the Xbox E3, showing, and it was really cool. Super stoked. I hope you guys are really excited, and let me know in chat what you think was the coolest announcement for you. Me personally, the holy cow moment was the backwards compatibility on Xbox One. That's just nuts.
Yeah.
I can't believe I'm gonna be able to now. I have to try to sell my 360 immediately.
Yeah.
It's gonna collect a lot of dust now.
I mean, this so far it's been just a day, but or I guess 2 days, but it's clear that the winners are the players.
And that's not just Xbox. Stuff. That's across the board,
for everything.
Right? For everything.
Yeah, it's pretty amazing. Pretty amazing. But let's jump into talking about what we're going to be talking about. So I'm running through right now the end product of where we're going to get to. This is pathfinding for an AI. We have this little guy right here, and he walks along this path. His goal is that goblin, so wherever I put that goblin, he knows how to get to it, and he climbs all the way up, and then he starts punching them when he's close by. So let's just to illustrate sort of how pathfinding works. And I'm going to talk about why you should care about pathfinding. Let's just put the goblin, say, right here. And watch out with the keyboard. Remember,
I'm making sure we don't go black.
Yeah.
That's my number one goal today, is
yeah.
to not have us go back.
So now this guy picks out a new path that brings him to the goblin, and then we'll attack the goblin. So, bam! Goblin being attacked. So, I actually have notes this time, too. Because we want to make this, really informative for you guys. So, pathfinding, just the idea of pathfinding it's a solution to what initially seems like a simple problem. Get from point A to point B. The problem appears when you have obstacles in the way. So you have a place like this that has a bunch of obstacles. So how do you intelligently move around these obstacles? Well, developers and creators have been coming up with a bunch of different ideas throughout the years, and there's many different ways you can use pathfinding, and pathfinding is basically your way to do that. So we're going to jump out of here. We are going to start from scratch. We're going to build all this stuff from scratch. And so what I'm going to be covering is pathfinding with waypoints and with using a graph. So what you're really trying to do with pathfinding is you're trying to graph a pathway along a number of points to get from A to B without walking into any barriers. So let's bring up some logic cubes for these quote-unquote points.
Man, I could use some pathfinding just for walking around the office. I hit my knee on everything. I wish I could avoid barriers all the time.
Okay. So we got, I like to make my nodes black, and I like to call them all node, because that is a term used in pathfinding, is each of these different things is a node. So these nodes are basically your points along the graph, helping you figure out how to get from point A to point B. You will want to place a lot of these things in your world. Let's actually create a logic cube here, and we're going to call this the node controller. And we'll just keep this the default white for now. So in this tutorial, I'm going to bring you through what pathfinding is, and then talk about a simple but very smart form of pathfinding that is called A-star pathfinding. There's a lot of different forms of pathfinding. A-star pathfinding is something that, for those of you who've been around the community for a while, it's something people have been asking about. How do you make this in Project Spark? And it's a lot simpler than you'd think, A-star pathfinding. It's using some pretty simple math. So once you understand just the concept of pathfinding, this will make it pretty easy for you to implement smart pathfinding for your AI in whatever you're making in Project Spark. So let's start by talking about these path nodes. So path nodes first actually became popular with first-person shooters back in the early 90s. Can you guess who was the champion of pathfinding? Thinking first-person shooter, thinking early 90s.
Quake?
Yeah, it's software. Yeah.
Okay.
So.
Yeah. You're looking for I'm thinking the game. Yeah.
Oh yeah. So they were the ones who first really started using this nodal pathfinding. Nowadays, a lot of games use something called nav meshes, but we won't worry about that. That's much more complex. We're gonna just focus on this nodal pathfinding because it's a pretty easy concept to understand. And to help actually illustrate this, let's actually add in some little barriers here. And Thomas, you're gonna have to tell me if what I'm saying is super confusing or not.
I think they're following along so far. We haven't lost anybody yet.
Yeah. 49. This is way too big. Okay. Let's shrink this down in size. So I'm just placing a few different barriers along here, so that it's not. You actually will have to use some pathfinding to get to the end, and let's make just like in my last one. Actually, no. This time, let's make a squirrel at the end. So the end product is a massive squirrel. That's what we'll do for the end product. This is my player. So we won't worry about him. We're not actually going to do anything to him. Because I'm just going to be walking around sort of observing what's happening in here. Oh, this squirrel is also moving. So let's delete all this stuff from the squirrel. Okay, and then let's also bring in my warrior guy, he is the one who's going to track this squirrel. And let's actually set this squirrel's team to be equal to 2, which we do here. There we go. Okay, so this guy he's going to be a follower fighter. Yeah, that's all cool. Okay, so where was I with nodal pathfinding? So the idea with these nodes, these are these black logic cubes. The idea is a creator plops down a node and then has a command for the AI of what node they need to go to next to reach the node that's basically closest to the goal. So let's just plop a bunch of these down. So we'll just place one here, one there. And with this kind of nodal pathfinding, the idea is you're plopping these down, and then every node is looking at, like, once you get to this one node, then it's looking at, all right, what's the next closest node to my target, my goal, and then the idea is you would move towards that, and that would be sort of your final, until you get to the final position. So nodes can be they're a nice easy solution because it's kind of easy to understand. You're placing these points, and then you know that a person can only walk to one of these points, and then they'll walk along to the next point. So the thing that you need to do now is the next important part of these nodes is, in order to know where to go, your nodes need to evaluate what is the best next node to go to. So when you get to one node, you need to then evaluate what's my next best point of movement. Where is the next best place to go to eventually get to this squirrel? So I've gotten to, let's say I start out going to this node. So, for instance, this way is further away from the squirrel, so that probably wouldn't be the best route, but this node seems to be the closest, so this will be probably what we go for. And then, so, when you get to here, then you say, okay, well, this is probably the next best node because it brings me closest to it, and this is probably next best one, brings me close to it, and then I'm there. And so that's what you're kind of doing with all of these nodes. You need each one to evaluate what the next thing is. So the thing that actually makes this pathfinding is you can tell a character to move to the next node and move from there to the next node, but that's not really useful unless you calculate in the final product. Like, telling a character to move from one node to the next node they can reach, that's all well and good, but it doesn't mean much without understanding that end destination in there. So how do you start understanding the end destination? And this is where the first idea comes in, and it's something called heuristics. So heuristics is a simple calculation to see basically a score or a number from that current node or the node you're evaluating to the goal point. So it's basically the distance from the next node that you might want to go to the goal node. And what does that look like? Let's go into here, and we are going to, it's a number variable, so we're going to call this if I can spell right, heuristics. And that would be equal to the distance to whatever the goal is from whatever the next node is that you're evaluating.
There was kind of a question from chat, and it's a pretty good question. So, would they be able to try to attempt this without having to place all those logic cubes around? Or would they be able to define that position by a vector, position, or?
Yeah, you can actually. I've been working on that on my free time. It's a lot more complicated because you need vector points, and you need those vector points to be stored. I'm actually getting rid of all these because I need to do one other important thing. So yeah, you actually can. You can save on your object count, not using up all these nodes in your world. It's much trickier, and it's going to require a brain that has a very sizable amount of code running in it. Because basically, what you're doing is, without kind of setting down these nodes themselves, you actually have to create a variable position in your world, and then that would be just like 1 point, and you have to set what the next one is, and so on and so forth. So drag and drop them that way in your world through vector points in a brain rather than this way. So it's much more complex than just kind of placing an object.
Yeah, this is kind of more plug and play. You're able to just kind of set them and look visually, right? Just drop the
exactly.
box.
You can visually look at that. There is actually a trick for how to use camera variables to do that, more plug and play. Maybe I'll tackle that at the end. But so the idea of heuristics is this is the kind of the first calculation you need to do, and it is just whatever the distance to the goal is from the node you're currently evaluating. So you've gotten to your first node. Now you're evaluating what the next node is you need to go to. So what you look at is you check every single one of the next nodes around you, and you look at which one has the highest, the lowest heuristic number, because it would have the number that's kind of the lowest number would mean that is the closest to the goal. And so then, by evaluating heuristics, you're able to say, this next node, this is the closest one of all the nodes around me to the goal. So I should go to this one, because this is going to take me closer to it. And then the next one after that, you do the same thing. So the problem with just doing things that way is that is called a greedy best first search. That's actually the official term for it, the greedy best first search. And it's called the greedy best first search because it only cares about whatever node is closest to the goal, and not the context of all nodes. So this means that sometimes what seems like it should be the shortest route actually could take a lot longer when you, say, hit a barrier, or just go, you end up having to go around a bunch of different things, where, say, you have kind of a wall right in front of the character, then you'll go there and you're like, oh wait, actually I need to go that way and then that way and then that way, when before you could have just gone that way. So so greedy best first is uses just heuristics, but it's not the best way because you're only looking for whatever's the closest to the end and moving towards that node. And that's why always going the kind of most direct route isn't best. Instead, you want your AI to have some form of planning. And so what you want to do is add in what's called a path cost component that adds your current distance to the next node's distance in the equation also. So in order to do that, I'm going to do a simple calculation that I am just going to call G, because that's what actually, if you look up the formula, it's called G also. So just to, if you ever look up ASR Pathfinding, the equation will have G in it. So that's why I chose G. But this would just be equal to the distance to the next node. So then you add this heuristic and this G together, and we're going to calculate something new called
H.
No, heuristic was actually H.
Okay.
So actually, what I wanted to do is I will just to make it easier, I'm going to call this the path cost. All right. So the path cost is then equal to simply G plus the heuristics. So then the path cost kind of looks together at two things. It looks for, all right, what is the closest thing to the final point of all the nodes around me, what's closest to the final point, and also what's closest to me. And by looking at those two things together, your AI actually is able to have planning in how they're moving, because they look for the closest route to them, kind of the laziest route for them, is actually, while also in the context of the closest route to the final goal. Those two combined together makes actually a pretty, like those simply two things together make a path cost that is actually pretty good. Like this, for the most part, will lead to the best path. It's not 100% of the time, but most of the time, those two calculations together lead towards the best path. And all you need to do now is look at that path cost, that number right there. And then you need to just look at that for all the adjacent nodes to the current node you're on. And then just move towards the next one and just keep on going until you get towards your target. So I've just gone over the this is just all the math. Let's actually go into how to actually put this into context. The very first thing I want to do actually is I want to go to my node here. And I am going to use a sensor people don't use too often, the vision sensor, because I actually like how controllable this is. So I like to do this in my nodes. I'll show you how you don't have to do this, but I like to basically, what I'm going to do is I'm going to calculate what each node can see, because I want to now, the first thing I want to do is I actually want to calculate who my adjacent nodes are. That's like the most important part. The most important part for any sort of pathfinding is knowing what nodes you can reach from one node and what you can't reach from another node. Because, for instance, say I place this right here and I place the next one right there. If this thinks that this is an adjacent node, well, that's not fun, because your character's just going to run to the wall, and then that's not really smart pathfinding. It's just them running to the wall. So the most important part by far is figuring out what the adjacent nodes are. So every node is going to have the same kind of C sensors as this one, so I just want to make sure this is good. That should be about good. I just like the C sensor because you can set like how wide it is. I like to make it super thin, and then you can also set how long it is, and you can even set the line of sight. But I'm not going to do that. I'm actually going to do some ray casting. This is probably a bit too long. So let's do something like that. Okay. So why did I just do that? So in my nodes, what I like to do, this is just a nice tip, is if you're going to be working around a lot with like one brain that's used in a lot of objects, don't put that brain in all the, don't directly code that brain in all the objects. Instead, have it in a logic cube somewhere, and then push that brain into all the objects. So I'm just going to say this, push brain that. And that way you can make changes to a central area, and it affects everything out there. So it's just much simpler. So I'm just going to start with this one node, and then after I do kind of all the stuff, then I will place all the other nodes around. All right, so we're going to just start with the once. And we are going to say the most important thing is to first just set who all my nodes are. So every node is part of this object set that is known as global nodes. And then we just need to actually do this, where that object set is incremented by each little node right there. So we're going to have global nodes increment by me. And just for debugging, testing purposes, I am also going to make them all visible, so you can actually see where every node is during test time. Obviously, when you finish your game, you want to make them invisible again, but I just want to do them visible for now. So I'm just going to do that. Okay, so there are a variety of ways to check, for each node to check to see what's around them. That's the most important part. Right now, you need to now set what your adjacent nodes are. So how does each node see another node? I like to do a way that is very weird. Definitely a lot of people saw this on the team and thought, that's a very interesting, weird way of doing it. But I think it's actually, works 100% of the time for me. So I very much enjoy this weird way of doing things. Because what I'm doing is
this is the spin, right?
Yeah, for 2 seconds, every single node is going to turn around. So they're all going to spin around quickly. So they're all basically going to be spinning around, looking at their environment. So they're all going to be kind of observing, like, what's around me, what's around me. So they're all going to be doing that. And then they are going to be, during those 60 seconds, they're going to be turning. And then they are going to be using this see sensor. And it's going to say that when they see something else that is part of that object set global nodes, then, all right, so it sees something that's a global node. So if you don't know much about the see sensor, so let's just illustrate this by rotating around, because you can see sort of how it's seeing. So it's sort of like, this is what's going to happen. It's going to be turning around, and it's going to be looking around. So if you don't know, default, the see sensor doesn't care if there are obstacles. It'll still see something. Mm-hmm. What you can do is there's a modifier here, line of sight, that excludes things that are blocked by terrain or other objects. I actually don't want to use that, though. I actually want to do some raycasting with this, because I need to do a bit of math here after that. So first, I'm going to see if I see a global node, and then I'm going to do a raycast after that. So I'm going to say when raycast hit from we're just going to say center to the thing that I saw. So we're going to refer to that thing that I saw by it. Center. So it's drawing a raycast hit, and a raycast hit is basically looking for, what am I hitting on my way to that thing, to that node? Am I hitting anything on the way to it? And this is looking for if there are any barriers in the way, basically. So let's just add our second node here to help illustrate. So we got our second node right here. So this guy, he's now looking around. He's gone. He now sees that node. That node has been seen, but it's behind a barrier, so he does a raycast hit out to that node, and it hits that barrier before it hits this thing. And so I basically don't want to add it unless it doesn't hit anything until it hits that barrier. So we are then going to say when global nodes contains it. Now the it is referring to whatever was just hit. So when you kind of always have to look at whatever's been referred to most recently in sort of what you're doing on the win side. So whatever has just been raycast hit, that is now it. And if it is part of this object set of global nodes, then we can do something. If it's not, we don't care, because if it's not a node, I've hit something that's not a node, I don't care. I don't want to add something. So I will just put here started to, then we have a new object set I call this adjacent nodes. So someone asked a good question in chat. Why don't you use detect instead of the spinning C sensor? You totally could use detect, right? You could use a variety of different sensors. You could just look for anything that is within 20 meters of me is all cool, or what have you. I enjoy using the C sensor more just because I just like the precision of like looking in a little vacuum area. But I think a lot of people use detect. There's a bunch of different ways to do it. The way you're just seeing is C, but most simply, or very simply, I could just say when instead of when C, when detect global node, then I do the same exact thing, and the same exact thing happens.
And you wouldn't have to spin it.
Yeah, you wouldn't have to spin it either. Yep. I just enjoyed spinning it because it
looks really cool at the beginning.
Yeah, pretty much. All right, so we're back here. So now, basically, once it's hit a global node, then we're going to add it to a new object set called adjacent nodes. And this is now going to be where things are referred to as this node is adjacent. The player can reach this node.
And the big thing, right? So you're not where your other global set of just nodes is a global variable, and then this is just for that node. So each node is keeping track of its own adjacent nodes.
Exactly. Mm-hmm. Yes, that's a really important point to bring up. There isn't a global here, so that means this is a local object set of adjacent nodes. That way I can refer to each object, the things that are part of its adjacent nodes. And then I want to, so this runs for 2 seconds or 60 frames. After 65 frames, basically five frames after that's done, then I just simply want to switch page. And I want to do that so that, even though this is only 9 lines of code, it's still 9 lines of code, and if you have a few hundred nodes, that's a lot. It adds up to a lot of lines of code that are kind of sitting there and running, or not running. Check and see if they're running. So whenever possible, you want to switch to a page with no code. If this object has stopped doing its thing and doesn't need to worry about the code, it helps make things more performant. So after 65 frames, I switch to a page that has nothing on it. The other thing I want to do is, if you're dealing with elevation, this gets to be tricky. If you have, say, your target's up here and you have like a ramp going up there, and then you have kind of a node up here, you want to kind of calculate, can you reach this thing that's up here? And there's a bunch of ways to do that. I'm not going to get too complex with it because you will need to do quite a few calculations, but I'll quickly show you one way to easily check. What I'm going to simply do is check to see if kind of my angle from this point to this point is greater than 45 degrees, then it's probably too high and I probably can't reach it. So to do that, I am simply going to set a vector variable that I'm going to call height reference, and I'll explain what that is in just a sec. So I want to set this to be equal to the hit position is the node that it has hit, basically. So I just want to do that. Don't worry, I'm going to explain this once I've actually gone through and added all the different vector points here. And then y is equal to, instead, this object's position y. So what this is doing, do I have a triangle? Can you give me a triangle? Because I'm using some trigonometry. Yeah, let's do this. Okay, so let's see if this makes sense to you, what I'm doing by having this triangle here. All right, so let's get my node. So say I got one node here, and I have one node up here. In order to calculate the angle between these, you also need one more reference. You need to build a right side triangle. So everyone who remembers trigonometry, or maybe you haven't even taken trigonometry yet, you're learning some trigonometry. You want to build a triangle, basically, that you can reference to find an angle. So you have you already have your 2 points, and that is reflected by, this is the node you're currently at, so that's position. And I'm doing a raycast hit. This is the node you're looking at, that's hit position. You need to create a new vector point that's basically this thing right here. And that's what I'm doing right here. And now that I have the position, I have the hit position, and I have this kind of what I'm just calling height reference. It's not a technical term, it's just a term that I came up. Then I can find out what the angle is. So I'm going to create a number variable called angle. Now I'm going to set that to be equal to the, I believe, is it in modifiers, math? I always forget where this is, but just type in angle between. So I'm looking for the angle between then the this height reference minus the position, and then the hit position minus the position. So this refers to all three of those points and is able to come up with an angle between by looking at that height reference, by looking at the position of the current node, by looking at the hit position, which is the position of that current node, and then you're taking out the position of your current node from both of those, and that gives you an angle. And then what I can do is when an angle, now when the angle is less than 45, only then do I add in this thing to adjacent nodes. So just like that, I've now excluded anything that would have an angle greater than 45 degrees.
Just to make sure I'm reading this right, so on this guy, you're evaluating this right here, and then you're doing another. So you have those two positions.
Yeah, so actually, so technically, to make it a bit easier to read, I could just put these in brackets.
Okay. Because angle between, because it's just looking at two, so you just like put them right next to each other. But
yeah, exactly. Because you don't have to put things in brackets in Project Spark. We do kind of the parsing for you. But to make it a bit easy to read, it's basically this.
Yeah.
So it's looking at the
that
angle.
helps my brain a lot.
Yeah, it's looking at the angle between the new place, the height reference, minus the position, and then the angle between that, and then the angle between that, and then the adjacent node, the hit position, minus the position. And so that's kind of basically creating a kind of central point here and there, and then you're able to find out what this angle is right here on this thing. So hopefully that makes sense to you. Vector math is cool, guys, if you know it.
It's really powerful.
Yeah, and thanks to user Instant Kafka who put me on the right track with this. I actually was having issues kind of referencing this in the right way, and he helped me troubleshoot it. So thank you to Instant Kafka for helping me with that. And then also to Chris Donsante from our engineering team telling me how to make it better too. Like he looked through all this and said, okay, here's how you make this 10 times better. It is. With just all of the stuff with pathfinding. Okay, so that's it, guys, for your nodes. That is all you need to do. Now your nodes, to run through one more time, they all kind of move around. They see what nodes are around them. They do a raycast hit. If the raycast hit hits that node, then it calculates what the angle is between the current node you're on and that node. If that angle is less than 45, if all of those things happen basically, then yes, that is an adjacent node. That node is cool. It is part of my adjacent node group. And every single node does this for the first 2 seconds. So what that means is technically during playtime, if another barrier comes in, your nodes only check during the very first 2 seconds. So
they're not like dynamically re-evaluating its adjacent
so very
nodes.
very easily you can just make it so they check that maybe like every minute or so. You don't want to have it happen
Or,
too
you
often.
know, if you have an environmental change, just toggle that to happen as soon as the stage
Right.
changes.
You don't want to have it happen too often because you're having a lot of raycasting. And the more raycasting you have, the slower things can get. So because you're having a lot of raycasting, the less you can do it, the better. And let me just make it so I kind of actually want to make it so you like just can't go here. Like, bam. Just like this is just not a cool place to go.
Gotcha.
So
Cool. And did you want to throw any nodes like at the top?
oh, like tops of these?
Yeah, to throw it off.
Sure.
Or to make so we can see that they don't evaluate as like adjacent nodes.
Yeah. The only thing that I was actually experimenting with earlier is like technically the angle from this to this is probably less than 45 degrees.
Oh, it is, yeah.
So it might actually.
On that one for sure.
Yeah. So, yeah, I was actually just before we started, I was doing a calculation of sort of combining distance and angle together to make something that actually is even more useful. But we won't worry about that for now. All right. So
There's always better ways to do things, and we always
Yep.
keep experimenting, right?
Okay, so we have all of our nodes placed. We have all of the stuff for how basically the nodes check to see what's adjacent to them. Now we got to give logic to our AI. So we are going to call this the path controller. Okay, so there's your path controller. And this is the brain you add to your AI that needs to run along the path. So how I like to do that is I like to... So here I'm actually going to wait 3 seconds because I'm going to wait for everything to figure out what its adjacent nodes are. So by the way, with pathfinding, you probably want your game to kind of have the pathfinding happen for a few seconds before anything else in the game happens, or else stuff will run on paths before paths are even made. Okay, so in my character, after a countdown timer of 3 seconds, we're just going to have this run just once. This person is going to add the brain. So we're going to say add brain. Wait, actually, no. Let's use a brain variable here. So let's use a brain variable called pathfinding. We are going to set it equal to add brain this. And now I can refer to basically have this pathfinding brain that's called this brain variable pathfinding. So it allows me to easily kind of toggle that brain on and off.
Oh, cool.
So there you go. That's a brain variable. That's how you can use brain variables in your game. All right, so you got your path controller. So this is kind of what runs for your character to get over to the goal. So we want a few things to happen once. They don't have to happen once. They can happen oftentimes. But the important thing is we have a goal, and we want to know what that goal is. So in this instance, the goal is a squirrel. But maybe you just constantly have the goal as equal to, like, my enemy. And that doesn't run once. That continues to run. Here, we only want it to run the one time because the goal is just a squirrel. That's, like, the only thing we care about. Then also, under here, we just simply want to start off by just knowing what's the very first node they walk towards. And that won't use any complex math or anything. It's just simply going to look at, all right, whatever is the closest thing that is a node.
Go there.
Yeah, exactly. So, nearest object. Oh, I want this to happen on the win side, don't I? Yeah. So when global nodes nearest object, then we are going to use this thing that I'm going to call current node, and that is equal to it. So now we have, we know what our goal is, and we know what the very first node is that we need to walk to. It's just the closest thing that is part of these global nodes. So I actually only have one movement happening the entire time in my character. I just move toward current node, and I want to set a minimum distance of 0, so let's keep on running, because default you have a minimum distance of 1. And also I want to set without deceleration, so they won't start slowing down when they get to the next node. And I'm just going to say like maybe at speed 0.8. So it's like a leisurely jog. You can obviously change that. Now the only thing you need to do is update that current node. Like while it's running, just update whatever that current node is, and your character will keep on running towards that. So how do you do that? So you do that by running lots of stuff. And it starts with when your distance to the current node is less than 0.5 meters. That's when you decide what the next thing is you need to run towards. So we're going to actually first start out with, we have to use this thing called next node. And we're going to start out with actually setting that to be equal to nothing, because we're actually going to reference this later on. Okay, so we are going to first evaluate that current node, its adjacent nodes. So this runs through every single adjacent node to that current node. Go back to the node controller, and basically that's everything that this current node can reach, or you can reach to from this current node. So it gets all of that, and then it evaluates something on every one of those. So we're going to say that it's, first we look at heuristics. We're going back through the calculation I start out with. So its heuristics are equal to the distance to the goal from it. And that is its heuristic calculation. Then we do its the GX calculation, or the calculation of basically just the distance to it. That's just what your distance is to that thing. And then you combine both those together to create
Path cost.
Exactly. Its path cost. And that will simply be its heuristic. Very important you add it, because you want every single item to store its values independent of each other, or when you're running through everything, if you're storing it in yourself, it's just going to keep on rewriting and overwriting itself. Plus its GX. Okay. So I've gotten all this stuff. I've calculated basically my path cost. Looked through all my adjacent nodes. I now know the path cost of them. So now it's a simple task of knowing what the node is with the lowest path cost, and then saying, okay, you're my next node. I'm going towards you. So you do that actually with, now this actually comes from user Mescad, who actually, I was doing things, my original code I had was doing it in like 4 lines. He condensed this down to 1 line. So yeah, I actually had 2 different people kind of from the community taking a look at this, making sure it all look good to them.
That's cool.
Okay, so when the let's see, current index. Just going to type this in. All right. When the current index is not as time is equal to 1. So the current index is basically where you are in this for each of loop. So this means basically when you're in the first item in that loop, because you want to start with the first item and go through every single item. Then we are going to call a new thing called smallest cost. And the smallest cost is going to be equal to its path cost. Then underneath here, we also say that we get this next node thing. And next node is, we're going to say that next node is equal to it. And then we're going to add another line here that looks for, let's see. Okay, so the else is basically saying when it's not current index 1. And we're looking for its path cost is less than the smallest cost. Then smallest cost is now equal to its path cost. And then we put under here, I'll be going through this line again, or I'll be going through this line when I'm done reviewing it so you understand what I'm kind of doing here. So next node is equal to it. And then I run all of this. And after all this, then I just say that my current node is now equal to my next node, because this has all been run. Okay, so what are lines 10, what the heck are lines 10 through 13 doing? All right, so line 10 starts out with the first item in this index. And what is this index? This index is the adjacent nodes of that node you're on. So it starts out with the very first node in that index. It sets the smallest cost to that node's path cost. It also sets the next node to be equal to that first node. Then it's looking for, all right, if the index isn't equal to 1, basically everything besides 1. So it's looping through it, and then it's saying if that node's path cost is less than the smallest cost, and we set the smallest cost here equal to the first node's path cost, then the smallest cost is equal to its path cost, and the next node is equal to it. So it'll run through each one of them basically, and what it's going to end up with is the smallest cost is going to be equal to whatever has the smallest path cost, and then it's going to end with that thing being set as the next node, and then we just say current node equals next node. And then you go all the way back up here. So this all happens, by the way, everything from line 5 all the way down to line 14 happens in one frame.
Yeah.
So this all happens in one frame, and then the current node is equal to the next node, and you're still running towards your current node. So within one frame, your current node switches, keep on going.
Gotcha. So to like visualize it, at least this is like helping me think about it. So for like the lines 10 and down, like good scroll down for the code.
Yep.
So like going through that and basically comparing the path costs, your first thing, okay, you just like are going through each one and say, you go to the first one, you say, okay, you have the smallest one, now take you, now look at you, do you actually have the smallest one compared to that one? If not, drop you, you're the new one.
Yep, exactly.
You go through the list like that and keep comparing it. So no, that makes sense. That's cool.
Yeah. And then just for helping with kind of debugging, I'm going to do a hologram on whatever the next node is so that I could kind of view this calculation. And then I can just, so for instance, I want something to happen to my character when they're at that squirrel. I want this guy to punch them. So let's go back in here. And I can just simply say when the distance to the goal is like less than 10. So I'm less than 10 meters away from the squirrel. Then I can
kill the brain, basically.
Yep. I can remove brain, pathfinding, and then I can switch to my next page. And the next page is where I have all the default follower stuff on.
So this guy's like a nice guy. He's gonna go look for his goal, which could be an ally, and then he gets to this ally and says, "Hey, I'm joining you now."
Or with Squirrel, because the Squirrel is on Team 2, he's gonna kill it.
Oh, there you go. Yeah.
All right, so let's see this in practice. Let's make sure I did everything okay.
So that was the spin. That was him finding the first one.
Oh, duh. Sorry, I totally forgot. These guys need to be templates. All right. All right, there we go. What? Why are you not running towards that, dude? I think you're missing what your next node is, dude.
He's ping-ponging.
Yeah, it's like saying, like, this is your next thing, man. This is the one you want to go to, but you're not. Okay, so why is he not going towards that? Yeah, it's interesting. Obviously it's something we did wrong in here. So maybe we just simply need to have this happen after current
updates.
node. Oh, wait. Let's do that. Boop. Boop. There we go. Okay, so he runs to that node. He's then got that one. He says, oh, that's not right. Then runs
so that one he appropriately evaluated that he couldn't go through that wall or whatever. And so he made his way around. And there he goes, switched over.
And bam! Oh, poor squirrel.
I was hoping he would be his friend. Instead he's his enemy. It's terrible.
Interesting thing from MESCAD is you can do a for each of loop, and as long as it's under 10,000 things you're looping between, you're all good. So, yeah, you can have a node have 10,000 adjacent nodes and it still runs okay. So just to make sure there's nothing I rigged here, let's move this squirrel around so we have to evaluate a new point to run towards. So let's put the squirrel there. Now we're going to everything's going to reevaluate itself, and then he now knows, all right, this is the fastest way to get to the squirrel, and I'm there. I'm here to help. Not really. You're attacking this girl. That's not helping. So yeah, there you go. We have. This is called A Pathfinding. Hopefully those concepts made sense to you. This will be up on YouTube for all those watching live. For all those on YouTube, hope you enjoyed what you watched, and let us know what else you want us to cover. I know pathfinding was something that a lot of people have had questions about in the past. So I hope this helps you. Actually, the most recent question we got on our forums for Tuesday streams was about pathfinding. So hopefully this explains to you how you do pathfinding. If you're curious, user Ian Elrod for his Q3MD7
Yeah.
thing, his Quake level, he uses something different than this. He uses it's different but similar in a way. He does use nodes, but he actually manually sets what node is adjacent to another node.
Oh, okay.
So you guys can totally do that.
Which is like more hands-on approach.
Yeah, it's more
right?
hands-on. Like what you can say is within each node, you say like this one is adjacent to me, this one's adjacent to me, this one is. You can manually set that in something if you want it to be super precise. Or if you want to make something plug and play and don't have to worry about finding out what you can reach to from what, you can do my method where you kind of spin around seeing what's nearby.
Generate it like yourself, the adjacent. That's cool.
Create your game as you play? Any Spark can do it. Spark, activate the portals.